Welcome to my video here on power series. This is our third day dealing with Taylor polynomials, Taylor series units. So power series is going to start to dive a little bit back into unit 10 stuff, which was all sequences in series. So power series, for the most part, looks like this. It's a series that has power, so it kind of sort of looks like a Taylor polynomial. So if you notice, it's got powers that keep increasing. So it says power 0, 1, 2. It keeps going on and on forever and ever. So that's really what a power series is. And then it's always centered at whatever the C value is. So for a power series centered at C, there are three possibilities. Either the series converges only at C, or there exists R, which is really the radius of convergence. Greater than 0, such that series converges for this value right here, or diverges in a certain. So either the series is going to converge or diverge based on what R is, or what the interval of R is, or the series converges for all real numbers. So it's important, though, that when we do this, we always use the ratio test for power series. Use the ratio test for the to test convergence. All right. So let's go ahead and this just talks a little more about the radius convergence down here, but I'll get to that as we do these problems. All right, so let's get to some problems here. So find the interval of convergence. So pretty much want to know when, like, dependent on what the x value is, when is this going to converge? Is it going to converge no matter what x is? Is it going to converge only for one certain x value, or is it going to converge in a little bit of an interval? So that's really what we're looking for right here. So what we're going to do here is the ratio test. So if you forgot, that's just when we find the limit as n approaches infinity of a n plus 1 all over a sub n. And that needs to equal some type of number. So it needs to equal, just say L, for it to converge. Okay. So if we're looking at a sub n plus 1, all we're going to do is we're going to just add an n plus 1 to each n value here. So it's got quite a few here. So we're going to find the limit as n approaches infinity of negative 1 to the n plus 1 plus 1, so n plus 2, because again, I'm doing the next term, times x minus 5 to the n plus 1 all over n plus 1 times 2 to the n plus 1. And it's all going to be divided by the original here. Okay, so what I'm going to do is I did this in the ratio test, and I'm going to just do it. So I just wrote it like this for the first time. From now on, I'm always going to write this as times the flipped version of this. So it's a little bit easier to start to pinpoint things. So this is really times negative 1 to the n plus 2, x minus 5 to the n plus 1, all over n plus 1, 2 to the n plus 1, times flip the original over n 2 to the n all over negative 1 to the n plus 1, x minus 5 to the n. So I'm going to need to start to pick this apart just a little bit here so that I can start to simplify this, and I'll just do that real quick right here. So this really turns into 2 to the n times 2. This really right here turns into negative 1 to the n plus 1 times negative 1. So you can kind of sort of see things starting to cancel out. And the last one I'm going to do here is this x minus 5 is really going to turn into an x minus 5 to the n times x minus 5. Okay, so I'm just canceling these out, writing the greens right above. I think that's it, because I'm going to have the n. I'm just double checking my work here. Yeah, I'm going to have the n and the 2. Got it. So we're going to have this cancel out right there. We're going to have this cancel out right there. And this cancel out right there. So the only thing on the original I'm left with is just n. So this is going to equal limit as n approaches infinity of, so we'll check my work here. Yeah, negative 1 to the x minus 5 is still left over, negative 1, x minus 5. And on the bottom, oh, no, and times n. On the bottom, I have n plus 1 times 2. And that's it. So now, let's remember, I'm going to find the limit as n approaches infinity, not this x minus 5. The x minus 5 and the negative 1 and the 2, that's all going to come out. And by the way, this is still absolute value. All right. So I'm going to pull out the negative 1, x minus 5, and the 2, the absolute value of all that. Okay, so I'm going to pull that out. And in just a second, I'm going to squash that negative 1 because this is absolute value. I'm going to take that out in a second. And I don't need the absolute value around the 2 because the 2 is always positive. Limit as n approaches infinity of n over n plus 1. Which, by the way, this portion right here is equal to 1. Okay, and then this is going to get squashed out as well. So I'm going to get x minus 5 all over 2 because the absolute value of negative 1 is just going to be it's just going to be positive 1. So now I have this right here. This is going to converge if this happens. So remember, this needs to be sorry, they're going to set this equal to needs to be greater than and less than 1. Sorry. So I'm going to add that little part right up here as well. So it needs to be equal to a number which is greater than less than 1. So this needs to be greater than or less than 1 for this to converge. I was just rereading what the ratio test conclusion needs to be. So let's go ahead and solve for this. I'm going to do a little bit of work right over here. So if we solve for this, I'm going to get the absolute value of x minus 5 needs to be less than 2, which by definition of absolute value, x minus 5 needs to be between negative 2 and 2. So if I add 5 to everything, I'm going to get 3 and 7. So x needs to be between 3 and 7. Now here's the key. Do I include the endpoints? We need to know, do I include the endpoints? I'm going to start to kind of spill over. This one's a lot of work here because I need to check the endpoints. So if x is equal to 3, does this work? So plug this back into my original here. If x is equal to 3, then I'm going to get the series from n equals 1 to infinity of negative 1 to the n plus 1 to negative 2 to the n all over n2 to the n. Okay, so this is going to rewrite as a little rewrite here in green. This is the same thing as negative 1 to the n times 2 to the n. Okay? So because of that, my 2 to the n's are going to cancel out. So my 2 to the n's are going to cancel out. Okay? So boom, boom. So I'm on the bottom. I'm left with just an n. And my negative 1 to the n and my negative 1 to the n plus 1, that's going to always be positive. Okay? Because no matter what the n value is here, like if n is odd, then this is positive and that's negative. So sorry, it's always going to be negative. And then if n is even, then they're also going to be opposite signs. So no matter what, these negative ones are always opposite signs. So since they're always opposite signs, it's always going to be negative. So this is actually going to be a negative 1 right here. Okay, so it's just reducing it from here down to here. And once we're here, this is a, take that negative out in front because that's really not that important to me. This is a p-series. I have p to equal 1. So this is going to be the harmonic, and so this diverges. So at x equals 3, we diverge. So this is not in R. That's not in the radius convergence. Okay? Now let's go ahead and check out when x is equal to 7. What happens? So when x is equal to 7, I'm going to be left with negative 1 to the n plus 1. If I do 7 minus 5, that's 2 to the n all over n2 to the n. Now this one's a little bit different. These 2 to the n is going to cancel out. I'm left with negative 1 to the n plus 1 all over n. Okay, this is alternating. So since this is alternating, this is also decreasing in magnitude. If I keep adding the n numbers, the bottom's going to keep getting larger and larger and larger. All right, so it's decreasing in magnitude. Because the denominator gets larger, the entire thing gets smaller and smaller. Magnitude just means absolute value, so I'm not caring about the negative 1 there. And the limit, as n approaches infinity, is going to equal, since the bottom is larger than the top, it's going to equal 0 of, say, a of n is equal to 0. Okay, so because of this, this is going to converge by the alternating series test. So I need to include the 7 in my ratio. So final answer here. So we did all this blue work really just for this little part right here. This is my final answer. 3 is less than x, which is less than or equal to 7, because we can equal 7. That's allowed. So all we did here in blue was figure out, am I including the 3 or am I including the 7? So since the 7 converges, I include it. Since the 3 diverge, I'm not including it. So this is my radius convergence. So part A, it took a little bit of work. Don't worry, part B and C, not so much. Especially since now we kind of got through the bones of the ratio test again. I'm going to go through the next one a little bit faster now. Okay. So same thing, checking for the radius of convergence. Hopefully I don't need that much room over here. Figure it out if I do. Okay. So for B, same thing. We're going to do the n plus 1, so the limit as n approaches infinity here of negative 1 to the n plus 1 times x to the 2 n plus 1 all over 2 n plus 1 times flip the original. All right, so what's going to end up happening here is we get some cancellations, because this is going to end up becoming in green 2n plus 3 factorial, which is really 2n plus 3, 2n plus 2 times 2n plus 1 factorial. So that's going to end up canceling with that. It's great. This right here is going to become, sorry, I'll keep this in green. See if we be consistent here. So this is going to be x to the 2n plus 3, which is really going to equal x to the 2n plus 1 times x squared. If you add those together, you're going to get the 2n plus 3. Okay. And then this is really negative 1 to the n times negative 1. So now we can start canceling things out. So that's gone, that's gone, that's gone. Oh, that's gone. That negative 1 is still there. That's gone. That's gone. So now I'm left with the limit as n approaches infinity. That negative 1 is still there. So I'm going to get negative x squared all over, looks like 2n plus 3, 2n plus 2. That's all I'm left with. Just double checking my work here. Yep. So I'm going to actually pull this again, absolute value. Almost forgot that. So this negative 1 part is going to come out. So I can just pull out the x squared version. So the x squared is always positive, getting rid of the absolute value. Limit as n approaches infinity, 1 over 2n plus 3, 2n plus 2. This is going to end up equaling 0. So, which is less than 1, by the way. So no matter what x is, this will always equal 0. So in this case, my radius convergence is going to be negative infinity to infinity, because this will always converge no matter what x is. All right, and then the last one. Sorry, I know this video is a little on the longer side. I'm going to kind of wrap this one up, hopefully a little bit quicker. Got it. So same thing here. We're going to find the limits. Just trying to make sure I don't have to write too much down for spacing. is going to be n plus 1, and then x minus 3 to the n plus 1 all over n factorial x minus 3 to the n. Okay, this is the ratio test here. This is really just n plus 1 times n factorial. And this is really x minus 3 to the n times x minus 3. So what I'm really left with here is the limit n approaches infinity of n plus 1 x minus 3. So this is always going to go into infinity no matter what. So this is absolute value. We'll just rewrite this so it looks nicer. This will be at the value of x minus 3 times the limit n approaches infinity of n plus 1, which this will equal infinity. So this has no radius convergence. So the radius of convergence is 0. We don't have anything that's going to converge outside of just the 3. So only x equals 3 will converge. Wait, where did he pull that one out of? If I plug in a 3, I get 0, and obviously a 0 series converges. So x equals 3 will converge. And those are my 3 situations that I had from the front page, whether I'm going to have an interval right here where I need to find out if the endpoints converge, one right here where it's always going to converge, and one right here where I just have one value converge. So power series will always converge. You just need to figure out which of the situations it is. And that's going to wrap up our video here for power series.